Welcome back. Today we are diving into a crucial explainer that will completely change how you view the physical world, and more importantly, how you tackle your Cambridge physics exams. We are mastering the core, non-negotiable physical principles of work, energy, and power. If you've ever lost marks because you used an everyday definition instead of a strict physics definition, this is exactly where we fix that. Every single mark counts, so let's get right into it.
Now, you might be wondering why we even need to spend time defining a word as simple as work. Well, look at how totally vague the word work is in plain English. We casually throw it around all the time. You might tell a friend, "I'm going to work today," or "I've done my homework," or "I was doing some heavy work in the garden." But here is the trap, and examiners love to test this. In physics, the word work has a very definite, uncompromising interpretation. We have to literally leave the English dictionary definition at the door if we want to truly understand how the universe operates, and if we want to ace these exams, we have to strictly apply the physics definition.
So, here is our roadmap for today. We're going to build your understanding logically, step by step. First, we'll decode the actual physics of work. Second, we'll explore energy as your capacity to act. Third, we'll lock down the absolute law of the universe, the conservation rule. Fourth, we'll analyze efficiency and lost energy. And finally, we'll tackle power, which is all about the rate of work.
Let's start with Section 1, the physics of work. Get ready to have your definition of effort completely redefined. This is a classic scenario that catches so many students off guard. Think about a massive Olympic weightlifter holding a barbell above their head. You look at them and assume a huge amount of work is being done, right? I mean, they're sweating, their muscles are visibly trembling, they are clearly burning through a ton of biological energy. But here is the trick. While it takes immense effort to lift those weights off the floor, which absolutely is positive work because a force is moving its point of application, simply holding them stationary overhead involves absolute zero work in physics. Why? Because the displacement is zero. No displacement means no work. It really is that simple, but it's a trap you must avoid on test day.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the physics. The absolutely crucial point here is that work is a scalar quantity that only happens when a force actually moves its point of application. This formula is your golden ticket. Work done equals force multiplied by displacement, specifically in the direction of the force. Now remember your basic principles. Both force and displacement are vector quantities, meaning they have a specific direction. But work itself? Work is a scalar quantity. It has a magnitude, an amount, but no direction. We measure it in joules. So when a force of exactly 1 Newton moves its point of application by 1 meter in the same direction as the force, exactly 1 joule of work is done. Basically, 1 joule is perfectly equivalent to 1 Newton meter.
But what happens when things aren't perfectly aligned? Imagine a tugboat pulling a larger ship. If the force and the displacement are not in the exact same direction, you absolutely cannot just multiply them together blindly. You have to resolve the force vector. You have to find the component of the force that is actually acting in the direction of the displacement. If you have a force F acting at an angle theta to the displacement x, the useful component of that force is F cosine theta. Therefore, the actual work done is F times x times cosine theta. What about the component of force acting at a perfect right angle, F sine theta? That component does absolutely zero work because the object isn't moving in that direction. Let's look at a quick example. A child towing a toy with a string at a 25-degree angle with a tension of 1.5 newtons, over 265 centimeters. First things first, always check your units. Convert those centimeters to meters, making it 2.65 meters. Then you take the horizontal force component, which is 1.5 times the cosine of 25 degrees, and multiply it by the 2.65 meters of distance. Crunch those numbers and you get a final answer of 3.6 joules of work done.
Moving on to Section 2. Now that we've nailed down what work is, let's talk about energy, the capacity to act.
Think about winding up a little mechanical toy or stretching a heavy coil spring. In order to stretch that spring, work had to be done on it. A force was applied and it moved through a distance. Now that spring is literally holding on to that effort. It is storing elastic potential energy, meaning it holds the immediate stored capacity to do work all on its own. When you let it go, it can launch a projectile, turn a gear, or slam a door. In physics, anything that is capable of doing work is said to have energy. Conversely, an object with zero energy is entirely unable to do any work whatsoever. Because energy is simply the ability to do work, it behaves the same way. It's a scalar quantity, and it is also measured in joules. This gives us a vital, foundational link to remember. Work done perfectly equals energy transferred.
Let's just pause for a second and look at the sheer scale of energy in our universe. Developing an intuition for these magnitudes gives you a huge advantage when checking your exam answers to see if they make logical sense. A single beat of the human heart requires about 1 joule of energy. Think about the moonlight hitting your face for 1 second. That's a tiny fraction, about 10 to the power of -3 joules. Now let's scale way up. Striking and burning a match releases about 1,000 joules. Eating a large cream cake, that hits you with 1,000,000 joules, 10 to the power of 6. A major earthquake unleashes a terrifying 10 to the power of 19 joules. And the rotational kinetic energy of the entire Milky Way galaxy, that is an almost incomprehensible 10 to the power of 50 joules. It's just a mind-boggling scale.
All right, Section 3, the conservation rule. It's time to uncover the ultimate law that governs all of this energy.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Now, back to our core concepts. You constantly hear the news talking about a global energy crisis, but strictly speaking, from a physics standpoint, that phrase is entirely inaccurate. The total amount of energy in the entire universe remains completely, perfectly constant. What we are actually experiencing is a fuel crisis. When we burn fossil fuels, which are basically just massive stores of chemical energy, we are transforming them. Inside a car engine, a portion of that chemical energy becomes the useful kinetic energy that moves the car down the road. But a huge, massive amount of it is wasted as thermal energy that just dissipates out into the atmosphere. The energy wasn't destroyed. It's still there. It just became totally useless to us. This is the supreme law of conservation of energy. Energy can never be created out of nothing, and it can never be destroyed into nothing. It can only ever be converted from one form to another.
The best way to understand this is to track the flow of energy like a detective. Let's map out a simple circuit chronologically, from a battery to a glowing lamp. Step 1, our journey starts with the chemical energy stored right inside the battery. Step 2, as the circuit is completed, that chemical energy is converted into electrical energy, or more precisely, it's the energy transferred by the electrical current as it flows through the copper wires. Step 3, when that current hits the filament inside the lamp, the energy undergoes another massive transformation. It turns into the useful light energy we want, but it also creates a lot of non-useful internal thermal energy, which is why the light bulb gets hot to the touch. Breaking a system down like this shows us a flawless, logical progression of how energy moves and changes costumes without a single joule ever actually disappearing.
Which perfectly leads us into Section 4, efficiency and loss energy. If energy is never destroyed, why don't things run perfectly forever? The answer to why batteries die and fuel runs out lies entirely in the concept of efficiency. During real-world energy conversions, a huge chunk of energy is basically wasted. It turns into non-useful thermal heat, usually because of friction. We design machines to change energy into a form we actually want, but no machine is ever perfect. If you roll a ball down a grassy hill, the exact amount of gravitational potential energy it loses does not perfectly equal the kinetic energy it gains by the time it reaches the bottom. Why? Because frictional forces from the grass and the air generate thermal energy which is lost to the surrounding environment. Efficiency is how we mathematically measure this reality. The formula is straightforward. Efficiency equals the useful energy output divided by the total energy input. You can write this as a decimal ratio or multiply it by 100 to get a percentage. Let's walk through a common exam-style scenario. Imagine a worker lifts a 480 Newton weight straight up a vertical distance of 3.5 meters using a system of pulleys. To do this, he has to pull on the rope with 200 newtons of force for a distance of 10.5 meters. First, we calculate the total work he put into the system. 200 newtons multiplied by 10.5 meters equals 2,100 joules of total input. Then, we calculate the useful work we actually got out of the system, which is lifting the heavy block. 480 newtons multiplied by 3.5 meters equals 1,680 joules. Finally, we just divide the useful output by the total input. 1,680 divided by 2,100 gives us an efficiency of 0.80, or exactly 80%. The missing 20% lost as heat due to the friction in the pulleys. Because we can never, ever beat the fundamental law of conservation of energy. Machines like this historical design for a perpetual motion machine are an absolute strict physical impossibility. Since energy cannot magically be created out of thin air, your useful energy output can never, under any circumstances, be greater than your total energy input. And that guarantees that efficiency can never exceed 100%. For centuries, inventors have been obsessed with building perpetual motion machines. Magical devices that supposedly run forever without needing fuel, or somehow output more energy than they take in. This drawing is a beautiful, complex piece of history, but it is doomed to fail. Why? Because it completely ignores the laws of physics we just established. In the real world, moving parts create friction. Friction generates thermal energy. That energy dissipates away from the system, and eventually the machine will grind to a complete halt. There are no free rides in physics. Let's tackle our final concept for today. Section 5. Power. This is all about the rate of work.
Let's think about this in terms of racing against time. Imagine an ordinary family car pulling up next to a highly tuned Formula One Grand Prix racing car. Let's pretend, just for the sake of the example, that they both have the exact same amount of chemical energy sitting in their fuel tanks. Theoretically speaking, they hold the exact same capacity to do total work. They could move the same mass the same total distance. However, when the light turns green, that Formula One car is going to absolutely empty its tank and complete that work in a fraction of the time. It travels much, much faster. Why is that? Because the racing car's engine is specifically engineered to convert that stored chemical energy into kinetic energy at a wildly accelerated rate. In physics, we say the racing car's engine is significantly more powerful. Power isn't about the total amount of work you can do, it's entirely about the speed at which you do it. Every second counts.
So, strictly defined in physics, power is simply the rate of doing work. And just like the word work, power is horribly misused in everyday conversation. You hear someone say a massively muscular weightlifter holding a boulder over his head is powerful. But remember what we learned in slide 5? If the boulder isn't moving, absolutely no work is being done. And if no work is being done, the power output is literally zero. Mathematically, power is defined as work done divided by the time taken to do it. It is a scalar quantity. We measure power in a unit called the watt, represented by a capital W. What is a watt? It's simple. 1 watt means you are converting exactly 1 joule of energy every single second. A tiny 1 watt LED bulb converts 1 joule of electrical energy into light and heat per second. A high-speed electric train, on the other hand, might operate at 1 million watts, a megawatt, meaning it is aggressively converting 1 million joules of energy every single second and accelerates down the track.
Now, this logically leads us to one of my favorite aha moments in A-level physics, and it's a derivation you absolutely need to be comfortable with. By substituting our earlier formulas into each other, we can prove that power is directly equal to force multiplied by velocity. Let's walk through it together. Step 1, we start with our brand new definition of power, P equals W divided by T. Step 2, we grab our definition of work from earlier. Work is force times displacement, so W becomes F times X. Plug that in and our equation becomes P equals F times X all divided by T. Step 3, take a close look at that X over T part. Displacement divided by time is the fundamental definition of constant velocity v. So we just swap x over t for v, and we are left with a beautifully elegant, incredibly useful final equation. Power equals force times velocity, or P equals Fv. This one single equation masterfully ties together force, physical motion, and time. If you can understand how we got there, you are well on your way to mastering this topic. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Before you click away, look around the room you're sitting in right now. Pick one machine. It could be a fan, your computer, a lamp. Ask yourself, what is its energy input? What is the useful output? And roughly, how efficient do you think it really is? Observe the world through this new lens of physics. You aren't just memorizing equations for a test, you are learning the underlying source code of reality itself. Keep practicing, keep questioning, and I'll see you in the next explainer.